Now, let us discuss Heisenberg's uncertainty principle. See, according to Heisenberg, it is impossible to determine position and momentum of a smallest particle like electron simultaneously and accurately. This is very interesting. He says that you cannot determine both the position and the momentum simultaneously, I mean at a time, that too accurately, with maximum accuracy. But why? Let us see. You know, this can be mathematically given as delta x into delta p is greater than or equal to h by n pi, where delta x is uncertainty in position and delta p is uncertainty in momentum. Of course, h is Planck's constant. N, of course, is an integer which takes up values 1, 2, 3, 4, and so on. Then this pi, of course, is a constant. But you know, this equation holds good when the value of n is 4. So generally, we take it as delta x into delta p is greater than or equal to h by 4 pi. Only when n is equal to 4, this equation holds good. I mean, gives proper results. We know that P is equal to M into V, just now I told.
Yes, sir.
Momentum is nothing but mass into velocity. Now the same thing, let me write for delta P. Let me write it as M into delta V, because mass is not going to change of a particle, of electron, of course, here. But velocity may change. So I've written delta V, but not a delta mv. Delta is a change. Delta V is a change in velocity. So delta P can be written as M into delta V. Now substituting this, I can write the final expression as delta x into m delta V is greater than or equal to h by 4 pi. So this and this are the important formulae. Now here, this delta V refers to uncertainty in velocity. Uncertainty in determining velocity is what it indicates. You know, we can actually explain this even this way also. Instead of momentum, we can also say, because we know that momentum is mass into velocity and Mass is not going to change, only the velocity is going to change. Let me write momentum or velocity of a smallest particle like electron cannot be determined simultaneously and accurate. Let me first give you the theoretical explanation. This gives you maximum clarity of why it is not possible to determine both at a time and that too accurately. Let's see. In general, if you want to see any object, suppose this is an object, you have to focus light whose wavelength is shorter than the size of the object. Only then the radiation strikes the object and of course it reflects back. This is possible only when wavelength of the radiation that is being focused on the object is shorter than the size of it. Otherwise, it will not strike. So here, let us just say that now we want to see the exact position of electron. Now that is what we want to see. Now let me just remove that this is an object. Let us just replace this by electron. Now we want to see the exact position of electron. I mean exact location of electron. For that, we need to focus radiation whose wavelength is shorter than the size of the electron. Of course, using wavelength shorter than the size of the electron, position can be determined. Because, this radiation strikes the electron and reflects back. And by recording this reflected radiation using some kind of experiments, some kind of calculation, we can actually determine the position. Position can be determined accurately. But, the problem is this wavelength is shorter. I mean, the wavelength of the radiation that is being focused is shorter. So this shorter wavelength radiation will have higher energy. We know that energy and the wavelength are inversely proportional because E is equal to hc by lambda. We know this. E and lambda are inversely proportional. So if lambda is less, then energy is going to be more. I mean, the energy of the radiation that is being incident on electron is more. Now, as and when this radiation of high energy falls on electron, this electron absorbs energy from the incident radiation in the form of photons. See, after absorbing energy from the incident radiation in the form of photons, it simply gets excited.
Yes, sir.
It gets excited. I mean, it goes into some other energy level. and goes into a higher energy level. And when it goes into a higher energy level, obviously its velocity is going to change.
Yes.
Velocity, of course, changes because it has gone into some other level. We know that velocity, of course, is 2 pi kz e square by nh. Velocity of electron is inversely proportional to the number of orbits. So when it goes into a higher energy level, its velocity decreases than what it was earlier. But anyway, velocity is changing. I mean, we are not in a position to determine velocity accurately. Therefore, velocity cannot be determined accurately. Position can be determined accurately using the wavelength having, of course, the shorter wavelength. But problem is we are failing in determining the velocity. So that is what the practical problem is. If you want to determine position accurately, you'll be missing its velocity because of this practical difficulty. See, because as and when the shorter wavelength radiation falls on electron, it absorbs energy in the form of photons and gets excited into a higher energy level. So its velocity changes. Therefore, we can't determine its velocity properly. Now you can say, if not a shorter wavelength radiation which has got higher energy, why can't we use something with a higher wavelength? Suppose if a radiation of higher wavelength is used, from our knowledge, we can say that obviously we will be missing the position, because just now I told that only when you use wavelength shorter than the size of the object, here in this case it is electron, then only you can determine the position accurately. But here you are not using a shorter wavelength radiation, you are using something with higher wavelength, so position is anyway missed. No problem, because wavelength is more as energy will be less. Okay, energy of the radiation is less. Now, when energy of the radiation is less, even if electron absorbs energy in the form of photons from the incident radiation, velocity is not going to change because it has less energy. It cannot get excited. So here, velocity is not changing. Therefore, velocity can be determined. You are missing its position, but you can determine the velocity properly. See, in the first case, we were able to determine the position accurately, but we missed velocity using light of shorter wavelength. But in the second case, I mean using light of higher wavelength or the radiation of higher wavelength, we are missing its position, but we are able to determine velocity accurately, because velocity is not changing. I mean, it is not going into any higher energy level because the energy of the incident radiation is less, that even if it absorbs, it cannot go into higher energy level because it is not sufficient enough to get excited into some other level. So this is the practical difficulty which is involved in the determination of position and velocity accurately and simultaneously. Yes, in the first case we could determine position accurately, but velocity was not determined accurately. You can determine both of them using light of shorter wavelength. You can determine position accurately, and of higher wavelength You can determine velocity accurately. Yes, you can determine both of them accurately, but not simultaneously. So let me just say that Heisenberg's uncertainty principle is in contradiction to Bohr's model. You know, it is because according to Bohr, you can determine position using the expression for calculating radius of the orbit. You can say in which orbit it is revolving. I mean, you can say at what distance it is present from the nucleus. The position can be known, and even velocity can be known using his velocity expression. I mean, the velocity expression that he derived. He says that you can calculate position, velocity at any point in time. But according to Heisenberg, it is not possible. Heisenberg's uncertainty principle rules out the possibility of determining position and velocity at a time, I mean simultaneously and accurately, due to practical difficulty. Position and velocity cannot be determined accurately and simultaneously. So this is the contradiction. Now coming to mathematical explanation. See, delta x into m delta v is greater than or equal to h by 4 pi. This is Heisenberg's uncertainty principle. Let us take two cases. Case 1 is if suppose delta x is 0. What does this mean? I mean if uncertainty in position is 0. When I say uncertainty in position is 0, means certainty is maximum, right? Uncertainty is 0. Certainty, of course, is maximum, 100%. When uncertainty in determining the position is 0, certainty is maximum, means you are going to determine position accurately. Accurate position can be determined, is what it says. Because certainty is maximum, means you are planning to determine accurate position. Let's see what happens if delta x is equal to 0. Now let us try for delta v. Delta v is equal to h by 4 pi m into delta x. I've written the expression for delta v. Then h
Yes.
by 4 pi m into, anyway delta x is 0. So something by 0 is infinite. Now look at this. When you are trying to determine the accurate position, look at what has happened. Now from this, what I can say is uncertainty in velocity is infinite. See, uncertainty is infinite, means certainty is obviously nil. Nothing, zero. No certainty at all. So I can simply say that velocity cannot be determined accurately. If
Yes.
suppose delta V is a zero, I mean, if you want to determine the velocity accurately, your delta x is going to become infinite. Same as in the previous case, if one is zero, the other one becomes infinite. I mean, if
Yes.
you want to determine velocity accurately, you'll be missing its position. If you want to determine position accurately, you'll be missing its velocity. So that is a practical difficulty. This is